my pleasure to have Charles Cao giving a talk to you this morning. Actually, I came across the papers that you guys wrote a few years ago, and I have read quite a few times. So I'm very excited to see you giving a talk about the kind of results you guys obtain. And you're going to be talking about, so before I say that, so Charles is a assistant professor at Virginia Tech, and he's going to be talking about a roadmap for quantizing quantum mechanics. So yours.
Thank you so much. Thank you so much, Guy. And thank you for the invitation. I would like to thank all the organizers for this really wonderful conference workshop. That I've learned a lot, and I feel inspired by a lot of the ideas that are being discussed here. And today I hope to share with you yet another one of how you might approach quantum gravity by gravitizing quantum mechanics. And I'm going to keep this talk on a very high level. And I'm going to conveniently sweep a lot of the details under the rug here, but please feel free to ask me afterwards or during the talk if anything is unclear. And so let me first say that our approach is a little different from the rest of the more well-known approach, like string theory or loop quantum gravity or group field theory, in the sense that we don't have a very short name. So our first thing was called space from Hilbert space, and you may wonder, well, that's too many syllables. Okay, so the second paper we wrote, we said bulk entanglement gravity. So then it has the acronym, which is BEG. We think that we should beg for your attention here. But in all seriousness, right, the crucial difference we would like to start with is the following: that when we're learning quantum mechanics in undergrad or in kindergarten, whenever you start, we tend to create a quantum theory from a classical one. For example, we talk about harmonic oscillators. We start with the classical description of harmonic oscillators, and then we quantize it. Similarly with quantum field theory, right? We start with the classical field theory, we quantize it. And of course, these structures will help us in the long run in many ways. But at the same time, when it comes to some areas of quantum gravity, we learn that as we learn more about quantum gravity, we learn that, wait a minute, these structures are starting to hinder our progress and make things a little more complicated, because we realize that these structures will go away anyway. And so the question then is that if we treat quantum mechanics as a fundamental theory, then why bring all this classical baggage with us in the first place? Can we then start with the bare bones description of quantum mechanics and emerge all these classical features, including space-time geometry and gravity, from it, right? So in other words, if I give you a vector in the Hilbert space, and then you have some Hamiltonian, or perhaps just the spectrum of the Hamiltonian, a very abstract Hamiltonian, that acts on the wave function. If you have a sufficiently complex system, can you recover the fact that perhaps the thing actually had a space-time hidden in it? And so that's going to be the objective of our program. So we call it, so if you try to do this, we call it gravitized quantum mechanics. So instead of quantizing gravity, you're going to do the opposite. Okay, and this is just I would like to echo back to Lenny Susskind's GR equals QM proposal. I'm going to say what GR is contained in QM, so it's a special system, a special quantum system. Okay. All right. So the roadmap is the following: that we are going to have, as we said earlier, we have some abstract vector in the Hilbert space, and then you have some quantum Hamiltonian. We're not going to talk about this piece today. We're just going to focus on the state. So everything is kinematic. You can think about it as a single time slice, or you can think about time emerging. Well, let's just go with it. And from the state, we're going to hopefully try to back out some structures related to geometry, related to matter, and then finally see whether we can get any features of gravity. Okay. So very roughly, the talk is going to come in three parts. So the first part is to do a very rough, get a very rough estimate if I just give you the state and I analyze data that's contained in the state, can I get a rough shape or dimension of some things that might look geometric? And after that, we will say, well, this is not good enough. So we also want some sort of semi-classical description of matter matter flowing on top of background geometry. And so this part, we're going to introduce a little bit more structure in the Hilbert space. It's called the quantum error correcting code. And finally, we're going to talk about what are some of the conditions you would need then to go towards gravity. All right. And finally, I'm going to speculate because this is a workshop. I think I'm allowed to pose some crazy questions or proposals. Okay. So let's start with the state. And I also want to be given some structure of the state or slash the Hilbert space. So let's assume that this to be our starting point, that I have a state in the Hilbert space that is factorizable. Now, you might object to say, how do you get these factors in the first place? Can you get something that's not factorizable? Well, the short answer is yes, and then I encourage you to check out some of the quantum meteorology or related works by my collaborators and colleagues, and but we don't fully answer the questions here, right? So there's a lot to explore still. But let's start. Let's suppose that you do have the state and you have the tensor product, and from the tensor product it gives you a notion of parts. Okay, and because you have parts, you can analyze how correlated are the parts to each other. So the thing we're going to compute is that now for each part, the smallest subsystem, you can compute what's the mutual information between two such subsystems, and you do it for all pairs. Okay, and the mutual information is, as usual, defined as the von Neumann entropy of a single factor, a von Neumann entropy of the other factor, and then you minus the von Neumann entropy of the union, and everything else is defined in the usual way. So after you've gotten all the mutual informations between all these parts, you can construct a graph representation. Now, this is not necessary, but just to give you a visualization of this representation, in that you can think about each tensor factor as a node in the graph, and then you can weigh the edges by the mutual information between these factors. Okay, so this is what we learned so far from the states. But now, let's say, are there structures in this correlation pattern that we can learn? Okay, and the guiding principle is inspired by what we observe in nature, in that things that are closer together seems to be more correlated, and things that are farther apart seems to be less correlated. So why don't we turn this observation on its head and say that, well, if you have two factors that have large mutual information, and mutual information is a measure of correlation. So if they have large mutual information, they have high correlation, let's say that they're closer, okay? And then if you have small mutual information and low correlation, let's say they're further apart. So by applying this principle, you can convert all this information data into some sort of distance data, right? You can then turn this whole graph into a metric space where you have the distances between any pairwise two of these nodes. Okay, and once you've done that, you can push this thing into an algorithm that involves a classical manifold learning algorithm that allows you to determine is the set of distances that relates all these pairs of points, is it anything close to the actual geometry? Is it close to an actual manifold? And the way we do it is by just trying to embed it into a manifold, right? And you ask, how good is the embedding, right? So if the embedding is good, then you say that whatever geometry that comes out of this structure is well approximated by a manifold. And so if you apply this algorithm, you chunk in all this data is going to output to another set of data. So you have basically some set of eigenvectors, and you have some eigenvalues. So the eigenvectors is going to tell you about the embedding coordinates of these nodes, of the nodes in the graph. Whereas the eigenvalues are going to tell you how extended are each dimension of the embedding. So let me give you an example. Suppose the state that you had was a state that I secretly obtained from a 1D spin chain, okay? But I didn't tell you it was from a spin chain. I just gave you a state in the Hilbert space, and I want you to tell me, okay, does this state have any sort of geometric feature hidden in its correlation? And then you run this algorithm, it will give you a set of these eigenvalues, and then you see that the eigenvalue distribution has the following. So there's one eigenvalue that's really large, and the rest of it is a lot smaller than that. So in short, this algorithm is telling you that there, in fact, is going to be a embedding of this graph that look almost one-dimensional in Euclidean space. But then there's also going to be small fluctuations around it, and that's why the eigenvalues are small. So if you convert these, if you use these as embedding coordinates, and then each of these blue nodes represents one of the graph nodes, you're going to see that it look more or less like a one-dimensional line. So that's what this leading eigenvalue is telling you. It looks like a 1D structure. And these subleading things, for example, in the second or the third dimension, is going to tell you how large a fluctuation it is that's away from this single-dimensional object. So if you repeat this exercise, suppose I give you some state that look two-dimensional, right? Then you're going to find, say, two eigenvalues that are really large and everything else is small. So, and then you do the embedding algorithm, you're going to indeed find that everything looks almost planar, but there are small fluctuations around this planarity. Okay, so that is how we get the rough shape and the dimension, for example, that you can extract from a quantum state. But now let's say that, well, any geometry that you extract, you can always define a geometry. How do you know that is a spatial geometry? And the solution we come up with is to try to see whether there's gravity in this geometry, and if there is, then perhaps there's more reason to call it actual space. Now, since we only have a single time slice, right, we have to be really careful what we mean by gravity here. So we can only talk about gravity that's also projected onto the single time slice. So let's try to see what happens. Okay, so suppose you've done the embedding and then you found out that there is sort of an emergent pattern that's consistent with almost a 2D geometry that's planar like this. Now you can ask, well, what if I entangled some factor that's over here with some other factor that's really far away? Okay, so if I do this, by acting some gate or entangling gate or entangling unitary, you're gonna increase the correlation between P and P prime, right? The two factors you just try to entangle. But because of the monogamy of entanglement, the more correlated you are between P and P prime, the less correlated you are, the less correlated is P between itself and its neighbors. Okay, and as we remember earlier from that picture, we said that less correlation means longer distance, right? So in this very heuristic argument, you can see that the distance being longer around its neighbors is going to create an angular deficit, which is curvature. Okay, so in fact, you can even show that because so there's one side of the equation is going to tell you that this decrease of correlation with its neighbors is going to create a curvature. On the other hand, this perturbation generated by the unitary is going to define for you a notion of energy. And this energy is called modular energy. As the details is not very important at the moment, but the point is that you can define a so-called entanglement Hamiltonian, and then this energy will be precisely given by the perturbation of the state evaluated with respect to the entanglement Hamiltonian. And in this way, you can actually show that there is some curvature that's proportional to some notion of energy, which is what you would expect if you project Einstein's equation into a single time slice. Okay. Now, okay, that sounds like a good story, but it's not a very precise story. So let's see whether we can make it better. All right. Actually, maybe I should pause for clarification questions. Yes. Okay, good. So in this one particular thing where we used to derive this particular relation, we use the monotonicity of mutual information. Yeah, okay, thanks. All right, uh, yeah, okay. So now we have a very rough idea where things are and what the shape looks like, and that entanglement perturbation can lead to gravity-like behaviors of generating curvatures related to some notion of energy. We want to do better, and we want to actually back out some notion, more precise definition of matter on top of the space-time geometry. We want to even recover the tensors of these, the metric tensors of the spatial geometry, and the question is, how do you do all this by just looking at a quantum state? Well, the answer is that, well, you don't. You want to introduce more structure, right? So the structure we're going to introduce is called quantum error correcting code. And since not everyone here is an expert in quantum coding theory, I'm just going to go over what the rough idea is behind a quantum code. So in quantum computing, we introduce quantum code mostly to protect quantum information against decoherence, against all sorts of quantum noise. And on the textbook level, the quantum code is simply a subspace of a Hilbert space. So you recognize this from our assumption, but now you can introduce a special subspace in the Hilbert space. So this Hilbert space, usually in quantum error correction, is called a physical Hilbert space. So you can think of each tensor factor as a physical qubit that you actually manipulate in a lab. And then you want to identify a good subspace within this physical Hilbert space such that it is robust against the errors that will happen that will be local with respect to the physical Hilbert spaces. So now let's assume that the state we're looking at actually lives in this code, or it's called a code subspace, and this state is called a code word. Okay, so that was what defines a code. It's simply a subspace in a Hilbert space. And as I mentioned, this is called a code subspace, and this is a physical Hilbert space. And the encoded information is the state. And I'm going to represent all encoded state with a tilde on top of it. All right. So now let me give you the more concrete example. Where you can see how this information is encoded. So, and a convenient way to identify this code subspace is through a so-called encoding isometry, or more generally encoding map, where it maps this information you would like to protect against error into the physical Hilbert space, into the space of qubits. And the image of this map is precisely the code subspace. Okay, so in other words, this logical Hilbert space over here is isomorphic to the code subspace C that we saw earlier. More explicitly, this is how you can construct the code. So if you have an encoding map, you can this map is basically a matrix that's gonna take a zero state to an entangled state like this, and let's call it zero tilde, and it's gonna take a one state to entangled state like this, then call it one tilde, and the code subspace is precisely spanned by these two states. Okay. Now you can also represent the same thing as graphically. So the red arrow is representing this logical Hilbert space, whereas the other four legs are representing the physical Hilbert space that consists of 4 qubits. So this is you put in some logical information, scramble it, and then outputs in the 4. Okay, and this is the same thing, but looking down from the top. Okay. So what makes it the error correcting code? So this is, you can see it through the following example in that it can correct for you an erasure. So what I mean by that is the following. Suppose you encoded your information psi into this code subspace. Now you lost qubit. So this is a state over 4 qubits, yeah? But now you lost qubit number 4. You no longer have any information about number 4. But no worries. From the remaining 3 qubits, you can always act a recovery unitary, U123, such that you will extract this information that you care about, which is psi on the first qubit, and you are left with some other junk that you don't care about. Okay, so this is what we mean by recovering unitary, recovering information and correcting errors, or at least in this talk, we're going to focus on correcting the so-called erasure errors. Okay. Yes. So So this idea, you mean this idea of extracting? Yeah, yeah, it is. Yeah, more or less. Yeah, yeah. Right, right. Yeah, 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 yeah. That's a great question. That's a great comment as well. Except it's very difficult to construct a linear map that gives you cloning because there's no cloning in quantum mechanics. Mm. You want arbitrary superpositions. Yeah, yeah, yeah. If you only have zero and ones, those correspond to classical codes, and that's why in classical, yeah, everything is fine. Yeah, 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 yeah. So, good. Other questions? All right. So if we stare at this QECC that we had before, we realize that there are two ingredients of interest. The first ingredient is, of course, the message that you would like to protect against error. That's the psi, which you can encode and you can decode, or you can extract from just the subsystem qubits 1 to 3. But you also have this remaining piece, and this piece encodes the entanglement resource that's needed to protect your information against error. So the rough intuition is the following. You have some entanglement resource. You have the message you would like to encode. You scramble the two, so the information about the message is going to spread not locally over all these 4 qubits, and then such that if you only have one of the qubits, you know absolutely nothing about the encoded message. Okay. So we're going to say later on that this message, this logical information that's robust against errors, is going to end up building for us our matter fields, and the other piece is going to end up building geometry. All right, so that's our message, and let's try to motivate why this message makes sense from the point of view of the ADS-CFT from holography. Now, I'm going to use ADS-CFT very minimally, so don't worry if you only heard about this and you never bother finding out what it is. But the point is that, in ADS-CFT, there is some boundary theory, right? It's called the conformal field theory, or the CFT. And then you can take a state in the conformal field theory, and that's a very intricate entanglement pattern. And from this intricate entanglement pattern, you can build a geometry at higher dimension. So, for example, you can think of the CFT, the state of the CFT living on the boundary of this manifold, which is simply a circle. But then the entanglement pattern from the degrees of freedom that are living on the boundary can help you deduce the fact that the bulk actually looks like a hyperbolic disk over here. So you can build toy models of the ADS-CFT correspondence that helps you understand how the geometry emerges. So here are some of the examples of such toy models where the qubits near the boundary are, of course, you can think of them as the boundary CFT degrees of freedom, or you can just think of them as degrees of freedom qubits that you control in the lab in some sort of trap ion quantum computer. Now, these qubits are entangled in an intricate pattern, and that entanglement pattern is captured precisely by these lines in the network. And what about these remaining red dots on the pentagons? These red dots represent the logical input and information. These are the things the message that you would like to encode such that they're robust against errors. So it turns out that there is a correspondence between a quantum code like this, where the encoding map is represented by this picture, and the low energy dictionary of the ADS-CFT correspondence. So it tells you how to translate something that's in this higher dimensional geometry into this lower dimensional boundary. Okay, so that's the rough idea behind these codes. And but the point is that you have now that you have an interesting pattern for both the boundary qubits and the bulk qubits, such that they both look geometrical in their own ways. Okay. And now let's look at what these codes can teach us. Okay. So coming back to these two pieces that we have for the 4-qubit code we saw earlier, you will see a similar pattern with these more complicated codes. Okay. So more generally, you can take a code that we saw in the slide before, and then you say, well, let me erase all the information. Let me just lose all the qubits over here. And then you only have the qubits that are on the boundary over here. Let's call that region A. And if you only have this state on region A, you still, no worries. There is a recovery unitary that allows you to extract the information that's all lying in the book. So they're all represented by these red dots over here. So all the qubits of information that are contained in this red wedge can be extracted in the form of rho. Okay, and then you're also left with some junk state that you don't care about as far as error correction goes. Okay, so this is just a definition of, if you have an encoder state and then you have only a subsystem, you can recover this. Okay, so what do these things represent? So the first thing is, as we mentioned, the bulk or the logical state. The second thing is going to be represented as the states that half of the bell pairs around all these edges. So each of these edges, you can think of them as the EPR state. And then the state over here is like you trace out a half of the EPR pairs, and then what you're left over is the chi state. So because of this tensor factorization, now if you compute von Neumann entropies of the state on both sides, you're going to get the following formula. Where on the left side, you're going to get the entanglement entropy of this subsystem that's living on A. On the right side, you're going to have two pieces of information. The first entropy is the entropy of the encoded information, because you only have a part of the encoding information. You don't have any encoding information of the stuff that's happening over here, so there could be entropy in general. And the other thing is the entropy of the residual cut, and then you can residual information, and thus you can show that is precisely equal to the number of edge cuts along this blue line over here. So this thing is geometric. It's playing the role of, say, a minimal surface in this graph. Yes. Yeah. Absolutely. Absolutely. Exactly. That's right. Exactly. That's precisely my next slide. Yeah. And I'm glad that you were already anticipating my next move. So, but let me just, for the rest of the audience, say that, well, this is a reasonable thing to call this geometry, because if you take a continuum limit of this in ADS-CFT, you recover the so-called RT or Liu-Takayanagi formula, or its generalizations, where the first term in the red box is precisely the entropy of the bulk information of the bulk matter field degrees of freedom. And the second term is precisely the area over 4G, where the area is the area of the minimal surface. Okay, so this is what I said. All right, so then, indeed, as Guy pointed out, that none of this really is special to ADS-CFT. In fact, we only use these, we just use these qubit models, right? They rely minimally on ADS-CFT. So we're using it just to draw analogies. But what if I take this correspondence to be more general? What if I just take the following, that for any error correcting code that corrects erasures, let me always take, you can always, from Harlow, you can show that it always satisfies this formula, this entropy formula, where the entropy of a subregion or subsystem A is broken down into one piece that encodes the logical information, and the other piece that encodes the residual information. And let's call this matter, and let's call this geometry. Let's see how far it gets us, right? And you can think of this as an analog of the generalized entropy as per Bekenstein. And you can take this geometric piece as defining some sort of proto area of between two regions if you have actually some sort of geometry that's emergent. And if you take this assumption as given and then apply it to the earlier program that I was telling you about, you just have a state, you have some rough shape of the manifold. Now let's think of those entanglements of different pieces A as different areas that slices through the manifold. You can use this information to back out a metric tensor. So you can say that maybe originally the manifold looks very similar to a flat manifold, but now using this information, you can actually update your knowledge and figure out exactly what the metric tensor is by figuring out what's the fluctuation around the flat manifold. Okay, and then there's a technique called the inverse tensor radon transform that allows you to pinpoint these things if an inverse geometry exists that's consistent with the data that you're given here. And if it doesn't exist, this procedure will also tell you how far away you are from an actual geometry. So we've done some numerics for in the context of ADS CFT, but in fact, this is actually easier to do in the context of flat space, except I don't have nice animation to show you in flat space, so I'm going to show you one about hyperbolic space. So this is one component of the reconstructed metric tensor, the metric perturbation on top of a background. And this is for some spin chain that generates some sort of entanglement dynamics, and you can essentially figure out that there are some metric perturbation captured by this plot here. But the important bit is that number one is doable. Number two is that from this algorithm is going to tell you how well your reconstructed metric fit the entanglement data that I was feeding into. So if it has a good fit, for example, you feed in some sort of data that's consistent with an ADS geometry, for example, pure ADS or a thermal ADS, you're going to get very small geometric data. Very small errors on the quality of the fit. Whereas if you have something that's clearly bad, for example, you have some large mass deformation that deviates you away from a CFT, or you have some local quench or some sort of disorder. It's gonna be on this higher end of the spectrum here. And depending on what the error is, you can try to figure out whether the data you're given actually describes the geometry or not. So just to give you an idea what non-geometric things look like, this is what will happen. So in this picture, we essentially superposed different black hole geometries at different temperatures. And so this is the plot of the reconstruction error. So the larger the error, the less geometrical something is, according to our definition. So as soon as you turn on the superposition, you see that the error jumps, and then when you turn off the superposition, the error comes back down again. So on the left, you see that at first you see some sort of thing that's very clumped in the middle. So it looks like a thermal box of gas or whatever, like things that want to stay in the middle. But then as soon as you turn on the superpositioning, is immediately dominated by these reconstruction artifacts that it tells you based on the errors that none of these is physical. Like this is all just trash and you shouldn't believe any of this. But then as you turn it off, everything comes back down, looking into like a geometrically local thing again. Okay, so just some examples. All right. So this is how we can make geometry more precise by backing out the metric tensor and also telling you how good is the metric description of the geometry. But it would be nice to also say something about gravity, right? So let's see how we can do that. And I would like to take the following stance by first saying that well, if I just hand you a generic complex quantum system, chances are you're not going to see anything that remotely looks like gravity. So instead, let's just assume that suppose you really end up emerging gravity in these systems. What are the necessary conditions that your quantum system has to satisfy? And to do that, let's work backwards, right? Suppose you do have a system in which linearized Einstein gravity is satisfied. But since we have a single time slice, we really just ask whether the spatial projection of the linearized Einstein's equation is satisfied. So you start with a system that satisfies this equation. And then let's do a so-called radon transform on both sides of this equation. So a radon transform, if you recall, is sort of like taking X-rays, right? So you integrate along some function, along some line over here, and then you do it for all the different angles. So here there's a tensorial generalization of the radon transform you can perform. And actually, in those cases, everything is scalar, but you can perform this kind of radon transform, and then you can just convert this linearized Einstein's equation or linearized Hamiltonian constraint into a equation that depends on area perturbation, where it descends from the curvature perturbation, and you will get also a energy perturbation that descends from the perturbation around T, the stress energy tensor. And this energy perturbation, this HQFT is so-called the modular Hamiltonian of the quantum field theory. So what you let me not go into the details later on. We can talk about it. But the point is that if you apply what we had earlier, this assumption that area is given by some entropy data, and you can also apply a so-called a well-known equality in quantum information is called the entanglement first law, which says the modular Hamiltonian, the first variation, the modular Hamiltonian is in fact equal to the first variation of some entropy. You can turn this whole thing into an entropic equation, and the entropic equations tell you that there's some geometric piece of the entropy plus some matter piece of the entropy, and the two things sum to zero. Yes. No, no, you don't have to assume this is general QFT. So this is different from Jacobsonian entanglement equilibrium. What would it be represent? Oh yeah. This is not yeah. So this would be T00 integrated x and then integrated in this entire half plane. Yeah, because of radon transform actually. Yeah, good. Other questions? All right. So just to pretty up everything, so with the equation that we got earlier was if you have linearized Einstein's equation in, say, around flat space, you're going to get this kind of equation, where it says it has to satisfy an entropic equation that geometric entropy plus matter entropy sums to zero. You might recall that this looks very similar to the Jacobsonian entangled equilibrium condition, where you have the UV entropy plus the RI entropy equals zero. This is only for experts in the audience. But you can notice that there is some similarity between the UV and geometry, right? This is whatever thing that builds the underlying geometry is, I suppose, what builds spacetime is more UV, and whatever builds matter field is more IR. So it sort of matches up. And you can see that there's also a similarity with the new Takeyanagi formula, which is needed, which is actually equivalent to the linearized Einstein's equation on ADS space. You can see that there's almost a one-to-one correspondence, except we pick the boundary condition where the boundary conditions give you zero. Okay. So this is echoing back to our earlier observation from Guy that, yeah, everything looks like it's general. There's the ADS-CFT. There's nothing special about ADS-CFT. Also, there's nothing special about flat space. There's something that's more general that's going on. Okay, so now I motivated this, and then I said that, well, we would like to find codes that satisfy these equations. Are the codes that we're working with satisfying these equations? Or their generalizations? The answer is actually no. Okay, so the quantum codes that we've been using for error correction on quantum computers actually are terrible for quantum gravity, in the sense that there are erasure correction codes that they're actually similar to QFT on curved background. Where logical information gives you matter field configuration, that's good. Entanglement builds geometry, that's also good, but there's no back reaction, so to speak, that whatever bulk state that you put, so whatever the state that you put into your logical Hilbert space, which describes matter, it's not going to change the underlying entropy of the geometry. Whereas in GR, we would expect that if I put in some matter that's more entropic or have different mass configuration, it will generate different geometric, it will back react on the geometry and generate different geometric entropy perturbations. So in the codes that we're looking at in quantum computing, matter is decoupled from gravity. However, so how do we get things that do back react? And to understand that, we come back to ADS-CFT as a toy model, as things that can lead us to a place, lead us into the promised land. So how is ADS-CFT able to do it? Because people have been able to do it. So what's missing here? It turns out what's missing is called magic. Okay. And I did not make this word up, as you can blame Alexei Kitaev. I think. So very roughly, the intuition behind magic is that if you think of entanglement as something that goes beyond classical correlation, you can think of magic as something that goes beyond the classical computation, even though, okay, this is not very imprecise. But let me just lie to you a little bit at this moment. So the magic we're going to look at here is also called non-stabilizedness. And let me give you a picture of what that means. So if you look at the Hilbert space of all possible states, there are going to be some oases in the state represented by these green dots that are classically easy to describe, and the dynamics that only takes you from one oasis to another is going to be classically easy to describe. These are called so-called stabilizer states, and then if you have some other quantum state that's outside these oases, these states generally contain a lot of magic. And the distance from some point in the Hilbert space to the nearest oasis is going to help you quantify how much magic there is in your state. Okay. So the codes we've been dealing with in quantum computing so far, and the ones I've been showing you, has zero magic. So they're living in one of these oases, but we want a code that doesn't. Okay. Just one more slide about what magic is, because I think everyone is very familiar with entanglement. Magic is somehow a stranger concept. So magic is a resource that's okay. So we don't quite know what magic is. It's very different depending on the definition, but we have a rough idea what it's supposed to tell us, and it's sort of in the general vicinity of these blobs, right? So first of all, we know magic is going to be an important resource for fault-tolerant universal quantum computation. It is necessary for quantum advantage, but it's insufficient by itself because you also need some sort of entangling gates. At the same time, it also quantifies for you some notions of quantumness, in that it's related to the negativity of the Wigner function. So the more negative you have in your Wigner function, the more magical it tends to be the state is. It's also related to classical hardness, and this is mostly an empirical observation, and it depends very much on how you do classical simulation. But you can find instances where, the more magic a state has, or more magical the process is, it's harder for Monte Carlo. It's going to be harder for these so-called stabilizer simulation, and in some instances, is also very hard for tensor networks. So these are, some of the classical things that we know that simulates quantum process. And the other thing that we know is that in quantum many-body states, there's a lot of magic. So for example, in conformal field theory, so one other thing is that you can sort of think of magic as being orthogonal to the entanglement as a different type of quantum resource. Okay. Now, coming back to the ADS CFT and magic, it turns out CFT is very magical. So this plot is showing that the magic of some subsystem in the spin chain called the Potts model, but you can tune the spin chain to approach criticality that's described by CFT. So as you approach the CFT, the magic peaks. And then when you go away from the criticality, the magic goes back down again. And in fact, you can show also that magic is related to some sort of gravitational back reaction in ADS CFT, in that if you, this is the familiar scenario of the Liu-Taganagi surface, right? It's saying, well, if you have a minimal surface that's anchored on the boundary, is given by some entanglement entropy on the boundary. But suppose you now put in, instead of a minimal surface, which doesn't have any mass energy, you put in some sort of cosmic brain that has a tension. So this tension will carry with it some sort of stress energy. And as you increase this stress energy, it's going to also back react on the geometry. It's going to change the area that's anchored to some boundary to the region. And the rate of change, the response function, how much this area changes, is a function of you adding stress energy, is determined by a non-local form of magic, which you can show. Okay. And provably, you can also show that this is not just true in the context in this way. You can also show that for general quantum error correcting codes in the Harlow picture, if you want something that can allow back reaction, that is, if you want something that has a non-trivial area operator, it has to have magic. Okay, so the natural next step is to then say that, well, why don't we just, yes. Yeah, 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 that's right. Yeah, that code will not have, it will have magic. Yeah, whereas the ones with trivial area operator doesn't, it doesn't, yeah. All right. So now we're gonna sprinkle a little bit of the magic dust on all the quantum codes that we have, which didn't somehow back react. Okay, so if you recall some of these codes, these are 4-qubit codes that are they're not magical. So we're gonna make it magical by just skewing it a little bit. And it turns out that is enough. So once you turn it into a magical code, you can find that there is the following thing emerges that if you fix all the states in some particular state, let's say the 0 state in the bulk, you can do a reconstruction and you can show that if you only have this part of the boundary, you can recover all the information in this red wedge. And if you have this part of the boundary, you can recover everything up to the blue wedge. And the boundary of these wedges is actually going to tell you where is the geodesic in this ADS geometry, and it's going to tell you that the geodesic go around here. So it's this is more or less consistent with the vacuum geometry of ADS. But if you now change it into a different state in the bulk, let's say a mixed state that has some entropy, you're going to find that if you run the same procedure, there's going to be a region where you do not recover the full information, and the geodesic is going to try to avoid the place that has entropy. So this is very similar to if you inserted some blob of dust, and then you've computed the boundary anchored geodesic is going to try to avoid this dust because of effects in gravity. And you can also verify this from an entropic point of view as well. So if you actually try to compute a definition of this proto-area entropy from the boundary, you can show that for a magical quantum code like the one above, as you turn up the entropy of the bulk, the area actually increases. So the picture that you see over here it can indeed be turned into a more precise entropy observation. In fact, we're doing this on an experiment with a bunch of people to actually verify this. Okay, and this is a simulation, obviously. So now you have a code where if you change the bulk state and actually where you change the matter configuration, it's going to give you some changes in the geometric entropy. And in fact, this thing is fully general. Okay, so what we saw here are just examples, but as you might rightly expect, these properties that relates magic to back reaction applies to a large class of quantum codes that there. So we're saying that for any exact erasure correction code, that's a huge class. That has a trivial area operator, which means that it doesn't back react. If you consider a general perturbation away from this code, you're going to find two things. First is that the geometric piece of the entropy is going to, in general, depend on the matter piece of the entropy up to some constant. And second, you are able to show that this constant is precisely a so-called tripartite non-local magic. So what I mean by that is that this is the magic that cannot be removed by any two-body unitaries at one time. So this is magic that's embedded very non-locally in the system. Okay. All right, so what about gravity? The take-home message that we're getting here is that if you want some sort of analog gravitational features, a necessary ingredient is this non-local magic. Okay, uh, so from a state perspective, what we've done by introducing non-local magic is that originally, if you have an exact code where you can recover the information perfectly, such that this corresponds to the matter, this corresponds to the geometry. Now, with a little bit of deviation, you do not perfectly decouple matter and geometry anymore. And in fact, there's always going to be some coupling. And that is intuitively consistent with what we want, in that if you have some matter configuration, you get one geometry, you have a different matter configuration, you get a different geometry. So in summary, what we have is the following, that we had this roadmap of saying, well, starting from a state, we want to get out its emergent dimensionality. We want to get out its metric tensor. We want to get out how we want to separate matter from geometry. And we want to make it such that it is generalizable to different kinds of geometries. And in fact, what we've done so far seems to indicate all of that, because all of these results apply very generally to quantum codes, right? You only rely on Hilbert space structure. You only rely on some sort of recoverability about this on the code. It's called erasure correction. And now we also know how to construct codes where matter entropy can trigger changes in the geometric entropy, which is a necessary condition for getting Einstein's equation. And now going forward, now that the geometric piece can vary based on the matter, we also needed to change in a particular way that's consistent with a linearized Einstein's equation. So in particular, it requires us to track down whether you can turn f of s into delta s, right? But perhaps you can think about other f of s that doesn't quite exactly give you Einstein's equation, maybe it gives you some other modified form of gravity. We also need time evolution, right? And then you need Lorentz invariance. And suppose all of these hold, and that the linearized Hamiltonian constraint, that is these entropic constraints, hold for all different time slices, then you can show that this is actually equivalent to the fully covariant form of the Einstein's equation, a linearized Einstein's equation. You can use the Feynman trick to show that this works. So there's a long list of work, and as all talks go, there's always a long list of work that you can do. But we colored some of the boxes green now, so there's hope. Okay. Okay. So last slide before I thank everyone for listening is let me just show you some speculations, because I felt inspired by the talks that happened in the past few days. The question is, can space-time emerge directly from space-time itself, emerge from entanglement pattern as a quantum circuit? So what I have explicitly is this example of the de Sitter-Mera picture. So de Sitter space, as we all know, is some sort of expanding universe. And then you could have local patches, right? If you have an observer over here that sort of follows some trajectory, it only has a causal patch in red that's sort of color in this tensor diagram. But you can describe the causal structure of the de Sitter space using a quantum circuit, right? Which is described by these isometric degree of freedom, which are quantum gates that entangle some new degree of freedom at every single time step. And these blue boxes are just small unitary gates that entangle two qubits, so to speak. But you can see that this thing has it has a causal structure, in that if you are an observer that will travel along this line, once you leave the horizon, which is boundary of this red wedge over here, you can never come back, no matter how hard you try it. But if you stay within this region, then you're safe, right? So this is sort of like the causal patch in the Sitter space. And you can also ask, the following question. So suppose I just have a quantum state that's living in the future. I don't actually have any of this explicit time dynamics. The quantum state described by this is going to be given by some scale invariant states, like the ground state of a conformal field theory. So in principle, there is information in the conformal field theory as entanglement that can help you back out all this, the pattern of the circuit. So can we then think about it as there is one moment in the present, and then I can, from the entanglement patterns of all the stuff that's happening in the present, back out everything that happened in the past, right? So this is another way of thinking about maybe time and space can emerge at the same time. So if you're interested, you can check out some of these other papers. But we don't, okay, we only talk about this, but none of that speculative stuff that I'm telling you. There's another thing about, well, I think we discussed the separation of the scales, and here I might, maybe I can speculate that the separation of the scales could maybe be given by a chain of subspaces, right? What we saw earlier is that if I have a single co-subspace in some physical Hilbert space, the physical Hilbert space is the full UV quantum gravity degrees free freedom, but the co-subspace describes some matter that's falling on some space-time. So in some sense that things over here is more IR and things here are more UV, right? So what if I just consider a sequence of such subspaces? This thing is called co-concatenation, and you can make it very concrete in the form of, again, a Mera tensor network, and then that turns out to also correspond to real space, a renormalization group. So there seems like there could be some interesting connections to be drawn there as well between RG and co-concatenation, and more generally just this structure of Hilbert space of containment of subspaces. And finally, maybe connections to quantum reference frames. It's more inspired by Emily's talk yesterday, even though I didn't fully understand it. So there is a connection with quantum reference frame with error correction in that if you identify the co-subspace with the so-called physical Hilbert space in the quantum reference frame, you can also identify the physical qubit Hilbert space with the kinematic Hilbert space. And then you would just have the code word is sort of like, this entanglement pattern is like you have some system and you have a reference and they're entangled. So maybe you can think about the system, the space-time serving as reference of how the matter is being really described or observed, and vice versa, right? You can use the matter to sort of as a reference to describe the space-time, or maybe you can think about this as some sort of decoherent state, and perhaps there's matter and the geometry is trying to observe each other. So all sorts of wild ideas. Perhaps I'm happy to talk about this further. So as a future outlook, okay, what we show you here is like a piece of road that has a lot of potholes and a lot of details that I glossed over and a lot of technical things to solve. But I would also like to point you towards this potentially brighter future that has a lot of good scenery along the road that, there may be a nice way of thinking about quantum gravity and an emergent space-time somewhere over here. All right. Thank you very much.